Welcome to this lesson on advanced, higher-level complex numbers for IB mathematics analysis and approaches. Today, we are exploring the deep connection between complex numbers and polynomial algebra. You will learn how to find roots of higher-degree polynomials using the conjugate root theorem, and how to calculate and visualize the roots of complex numbers using de Moivre's theorem. These concepts are vital because they bridge the gap between algebra and geometry. In the IB examinations, you can expect these topics to appear in Paper 1 for non-calculator proofs and in Paper 2 or 3 for complex problem solving involving geometric properties of roots. Let's begin with the conjugate root theorem. This theorem states that if a polynomial equation has purely real coefficients, its non-real complex roots must occur in conjugate pairs. Intuition tells us that since the coefficients in the final polynomial are real, any imaginary parts generated during expansion must cancel out. This only happens if we multiply a factor by its conjugate. For a simple quadratic, you've seen this in the quadratic formula. When the discriminant is negative, the square root produces an imaginary term preceded by a plus or minus sign, creating that perfect conjugate pair. This principle extends to any polynomial degree, provided the coefficients remain real. Let's apply this. We are asked to find all roots of a cubic equation given that one root is 1 plus 2i. First, check the coefficients: 1, -4, 9, and -10. They are all real. Therefore, by the conjugate root theorem, the complex conjugate, 1 minus 2i must also be a root. To find the final root, we construct a quadratic factor from these two roots. Using the difference of two squares identity makes this expansion much faster than FOIL. We get z squared minus 2z plus 5. Now, we look at the constant term. 5 times what gives us -10? It must be -2. By inspection or polynomial division, the final factor is z minus 2. Our three roots are 1 plus 2i, 1 minus 2i, and 2. Next, we move to de Moivre's theorem, one of the most powerful tools in complex algebra. It states that to raise a complex number to a power, you raise the magnitude to that power and multiply the argument by that power. In Euler's form, this is even more intuitive. It follows the standard laws of exponents. This theorem is essential for simplifying high-power calculations and finding roots. The IB syllabus often requires a proof of this by induction for positive integers. We start with the base case at n equals 1, which is trivial. We then assume it holds for n equals k. For the inductive step, we multiply the assumption by one more factor of the complex number. By applying the trigonometric compound angle identities, we see the arguments add together, confirming the result for k plus 1. We can also use de Moivre's theorem in reverse to find the roots of a complex number. If we want to solve z to the power of n equals w, we are essentially looking for the nth roots of w. Because the sine and cosine functions are periodic, adding multiples of 2 pi to the argument doesn't change the complex number w, but it produces distinct values when we divide the argument by n. This is why a complex number has exactly n distinct nth roots, corresponding to k equals 0, 1, 2, up to n minus 1. Let's find the cube roots of 8i. First, we write 8i in polar form. Its magnitude is 8, and it lies on the positive imaginary axis, so its argument is pi over 2. Next, we apply the root formula for n equals 3. For k equals 0, we get 2 cis pi over 6, which is square root of 3 plus I. For k equals 1, we add 2 pi over 3 to the argument, giving us negative square root of 3 plus I. For k equals 2, we add it again to get negative 2i. Converting back to Cartesian form gives us our three distinct roots. Let's look at the concept of the geometric interpretation of roots. The geometric properties of these roots are a favorite of IB examiners. All nth roots of a complex number lie on a circle centered at the origin, with a radius equal to the nth root of the original magnitude. Notice how the roots of 8i we just calculated are separated by exactly 2 pi divided by 3 radians. This symmetry means they form the vertices of a regular polygon. In this case, an equilateral triangle. Furthermore, if you add these complex numbers together, they will always sum to 0. This is a powerful property often used to solve high-level geometric proofs in Paper 3. In this exam-style question, we are dealing with a quartic polynomial with real coefficients. Since the coefficients are real, the conjugate root theorem must apply to all non-real roots. Because the coefficients are real, the conjugates of our given roots are also roots. This gives us the complete set of 4 roots for our quartic. Next, we form quadratic factors by grouping the conjugate pairs. The first pair gives us z squared plus 4. For the second pair, we use the difference of squares on the real and imaginary parts. This simplifies to z squared minus 2z plus 2. To find the coefficients, we multiply the 2 quadratic factors. This is much more efficient than multiplying 4 linear factors individually. Expanding carefully, we distribute the terms to get the full polynomial. Finally, by comparing the coefficients with the general form, we find the values for a, b, c, and d. One of the most frequent errors is applying the conjugate root theorem to polynomials with complex coefficients. If even one coefficient is imaginary, the roots do not have to be conjugates. Always verify that all coefficients are real before assuming a conjugate pair exists. Students often make sign errors when expanding the linear factors. Look at the mistake here, z minus a plus bi. The correct form is z minus a minus bi. Use brackets carefully, z minus the entire root. Grouping the real parts together, like z minus a in brackets, makes the expansion using the difference of squares much safer and faster. In complex numbers, z cubed equals 8 has 3 distinct solutions, not just the real number 2. If you forget to add the 2 kpi periodicity before dividing by n, you will lose the majority of the marks for the question. The IB curriculum heavily favors radians. Using degrees in your argument can lead to errors, especially in show that questions or when the result needs to be in Euler's form. Stick to radians unless the question explicitly states otherwise. In Paper 1, if you are given one complex root of a high-degree polynomial, check the coefficients immediately. If they are real, you have effectively been given 2 roots for the price of 1. This is a common shortcut IB examiners expect you to take. When multiplying the factors, always group it as a difference of squares. This results in z minus a squared plus b squared. This prevents the algebraic sign errors that frequently occur during expansion and saves precious time. Even if you make a calculation error, you can still gain method marks by clearly showing the general formula. Always write the general formula before substituting specific values of k. For roots of complex numbers, do a quick sketch on an Argand diagram. If your roots don't form a regular polygon centered at the origin, you know you've made an error. Examiners often award a mark for a correct diagram showing symmetry. Take a moment to pause the video and attempt these 3 questions. They range from a basic application of the conjugate root theorem to a more complex geometric problem involving roots. Once you have had a go, we will work through the solutions step by step. Let's go through the solutions for our homework questions. For the easy question, we identify the conjugate root and expand the quadratic factor. The difference of squares once again makes the constant term calculation straightforward. 3 squared plus 1 squared. For the medium question, we treat negative 16 as a complex number with an argument of pi. Applying the root formula for n equals 4, we find 4 roots separated by pi over 2 radians. For the hard question, we use the geometric interpretation. The nth roots of unity form a regular n-gon inscribed in a unit circle. By dividing the polygon into n equal triangles, we apply the area formula half AB sine C for each triangle and sum them up. First, the conjugate root theorem. Non-real roots of polynomials with real coefficients always appear in conjugate pairs. This allows you to factorize higher-degree polynomials efficiently by constructing quadratic factors. Second, de Moivre's theorem. To raise a complex number to a power n, raise the magnitude to that power and multiply the argument by n. This is most easily visualized and calculated using Euler's form, re to the I theta. Third, finding roots. A complex number has exactly n distinct nth roots. To find them, add multiples of 2 pi to the argument before dividing by n to ensure you capture all unique solutions. Fourth, geometric symmetry. The nth roots are equally spaced on a circle in the Argand diagram, forming the vertices of a regular n-sided polygon. Their sum is always 0. Finally, exam strategy. Always check for real coefficients before assuming conjugates. Use the difference of squares to expand factors quickly, and use sketches to verify the symmetry of your roots.